Hello and welcome in this new video where we will be leveraging all the key terms that we have introduced into the previous video. So if you remember, in the previous video, we have spent quite some time speaking about key terminology elements and refreshing our minds on important definitions. And the reason we did this is for the pleasure. Well, obviously it's a joke. The reason why we did this is because we will need all these key terms to help us build the modern data center fabrics and environments. Actually, they are like pieces of the puzzle that will all fit together to help us build our fabrics. So with that said, let's head to our slides. And the first one shows a very simple drawing where we will be presenting the key devices that constitute our modern fabrics. So the first thing I would like to stress is that this is not a two-tier topology. And by two tiers topology, what I am referring to is really the kind of legacy networks that we have extensively covered in the previous video. So in the legacy environments, we used to have typically a layer of L2 access switches, and then either one or two additional layers. So either a collapsed distribution / core or a distribution then a core. And in these two layers, we would have the routing functionalities. It is not what we are having here. What we have here is what we call a leaf spine topology. And obviously, each kind of those two devices has its own capabilities. So the leaves, they are responsible for connecting the end hosts. This is a host. I know, I have never been good in drawing. Anyway, and the way I like to see leaves is in a kind of collapsed access / distrib / core in comparison to the previous 3 tiers or 2 tiers. In fact, everything that we had into our 2/3 tiers is implemented at the layer of the leaf. It means it has really all the capabilities and all the functionalities to be able to perform locally the routing and the switching. So if we have devices that are attached directly to the same leaf and need to communicate with each other, whether they are in the same network or in different networks, the leaf do not need to reach out to anybody in order to be able to perform the routing and the switching functions. Then when it comes to the spines, well, they have also a crucial role into our environment because obviously we can see from the drawing that they connect the leaves between each other. It means that from the data plane perspective, they receive all the traffic between two leaves and they help into routing that traffic. And they also have a role in the control plane perspective that we will be exploring into the next slides. Now I think it is too early, but they will help into spreading the reachability information of the host all over the fabric. Just a small spoiler. Now for the last point that we see on this slide is the term close fabric. So actually, close fabric is the term that we use to refer to this very specific type of interconnections between the leaves and the spines. I'm not meaning the exact number of the spines that we see, nor the exact numbers of the leaves that we see, but really these kinds of topologies. And we will be explaining exactly what is behind this term in the next slide. But first, let me try to erase all this mess. And let's move to the next slide. So let's understand what is behind the term close topology. First things first, what are the types of links that we have between the leaves and the spine in the Cisco VXLAN, L2VPN, EVPN fabrics? Well, actually, it is really layer 3 point-to-point interfaces. We will see later how we configure them, but just to, to demystify and so that we are really on the same page and we talk about the same thing, this really nothing fancy about this interface. It is really interface Ethernet, for example, 1/1, no switch port, and IP address, whatever the IP address and the mask, usually it's /31. So it's really this configuration that we have there. Obviously, we will be adding a lot more configuration as we go on, but for the purpose of this slide, this is enough. So all these are the same kind of interfaces with the same bandwidth. And what this allows us to have is these key features functionalities. So we have a wide ECMP, unicast or multicast. Well, it's obvious we have from each leaf we have multiple links to reach the rest of the fabric. But really importantly, we have uniform reachability and deterministic latency. It means, so as we can see, every leaf has exactly the same kind of interconnections to the spine as all the other bodies in the fabric. This is very important. Why? Because this is very predictive. We know that whatever the hosts that need to communicate over or across the fabric, their path through the fabric will be always 2 hops. 1, 2. Whatever the type, whatever the exact path they go through among all these available links, it is always, so every end hosts are always 2 hops away from each other from a routing perspective, because we know that this is routing. But we will again refresh it in the next slides. So this gives us again a very predictable environment because it's deterministic and uniform. And this is exactly what we call a class topology. So just a side note, because in the last slide I was mentioning that it doesn't depend on the number of leaf of spines. Even if I have a very small environment with one spine and multiple leaves, then between every leaves I have exactly the same number of spines, which is 1, and same number of hops, which is 2. If I add a spine, one spine, then I will connect it like this. And again, I'm respecting through this uniformity of connection, a uniformity of reachability, and hence a deterministic latency. And for the last point, it is obvious that with all this redundancy, we can survive any kind of failure. We can survive a spine failure, we can survive a link failure. When it comes to the failure of the leaves, we say, okay, here we have host, each host is attached, single attached to each leaf. We are not surviving the loss of one leaf. How do we do? It's a very important point indeed. So the choice that I have made is that for all the first presentations of the playlist, I will assume that each leaf is a standalone. The solution to this issue is to configure the leaves as VPC. So instead of having each leaf as coming as a standalone, we use the VPC technology of Cisco in order to take 2 distinct physical boxes and make them appear as one logical box from the perspective of the outside. So we have seen this in the previous video, and we can completely use VPC in VXLAN EVPN fabric. I would even say that it is the best practice, the recommendation. Never use leaves as a standalone, always use them as VPC. But the thing is that VPC adds some complexity to the configurations and to the understanding. This is why I decided to not introduce them for the moment and consider all the theory from the perspective of standalone leaves each time. Again, we will be introducing VPC in the next presentations. Okay, so now let me clear all this and move to the next slide. Just to have again few words about the scalability. How do I scale out? So I can come out of ports from the leaves perspective. In that case, scaling out is very easy because I will simply add an additional leaf, and I will obviously connect it to all the spines as I have the other leaves being connected, again for the reasons that we were explaining and covering of uniformity and deterministic latency and so on and so forth. Now, when it comes to the need, so this is what I was mentioning here. If we need more ports, more capacity, we simply add more leaves. When do we add more spines? Well, it is typically when we need more bandwidth / more resiliency. Well, obviously here I already have a big number of spines, to be honest. Usually for most of the deployments, we have 2 spines. And then when we need more bandwidth, more resiliency, we add a 3rd spine, and then we can add a 4th spine. Side note, it's completely okay to have an odd number of spines. So 3, for example, there is no issue regarding this. It works perfectly. So this is what we mentioned, what we name as scale as you grow. And maybe you have also the question of what does happen if we run out of available ports on the spine? What is the way out? Because when we add more spines, if you want to respect what I have said, we need to connect all the leaves to them. So all the spines will have the same number of ports being consumed, right? So what do we do when we run out of spines? Well, this is not an issue. We will consider this fabric as being one single side fabric, and we can build over it using multiple solutions that have been designed by Cisco to address these use cases. We can either have another layer of spines, or we can leverage the Cisco multi-site solutions, for example. But this is an advanced topic that we will not be covering into this session. But just to mention that we have a solution for this. Now, let's move on with the reminder, or not the reminder, but seeing how the terminology of the previous presentation fits into our current building blocks. So for the underlay, let's see what's the purpose of the underlay exactly. And I hope that you remember this drawing that we have seen in the last section. So we have seen that when we have networks that leverage a segregation between an underlay and in the overlay, we have some edge devices that are responsible of first informing each other of the hosts and the networks that are connected behind them, hosts and networks. So they exchange the reachability information through the control plane overlay protocol. And then they are also responsible of building and maintaining the tunnels between each other. So this is from the perspective of a data plane overlay protocol. So 2, it is the data plane. So first, they exchange the reachability information of the end hosts in the overlay. And 2, they ensure that we can send frames and packets between the end hosts through the encapsulations, in other words, through the tunnels that are built and maintained between them. So obviously, in our case, the edge devices, it is the leaves. So it is on the leaves that we have the end hosts, and it is the leaf's responsibility to send the routing information, the reachability information to the rest of the fabric, and then also build the tunnels to reach the end of the fabric. But then you can say, okay, the title of the slide is Underlay, and I am speaking about overlay, like overlay control plane to spread the reachability information, and overlay data plane in order to ensure the reachability between the edges. So where is the underlay? Well, here comes the underlay. I like to start by explaining why we need the stuff before introducing the stuff, so that we see why we are having this kind of technologies being used. So we see that the leaves will need to have reachability for 2 purposes. We need to have reachability first to build the routing adjacencies in order to exchange information, and reachability also for the data plane, because we have seen that VXLAN is an encapsulation. So it will take the initial frame, it will add a VXLAN header, and then it will add an IP header with the destination IP address being the one of the remote leaf. So we need also reachability from a data plane perspective. Because I had prepared an animation, but I forgot to make it. So who will be in charge of the reachability of these devices? And here comes the underlay, obviously. So it is the underlay's responsibility to help with the reachability between the edge devices. So the underlay control plane protocol really is it's in charge of advertising the reachability of the edge devices, peering addresses, and the tunnel extremities. And by the way, I'm making the difference between the 2. And the question might come saying, okay, do we really have different addresses when it comes to peering versus extremities of the tunnel? And the answer is yes. Each leaf has multiple IP addresses for these purposes, and actually they reflect in the configuration in the way of loopbacks. We will be touching this extensively in the future slides. But for now, the key takeaway is that we have different IP addresses, different purposes, but all these IP addresses of the VTEPs, of the leaves, sorry, they will be announced across the fabric through the underlay control plane protocol. And speaking about underlay control plane protocol, what are the control plane protocols that we can leverage? So for this point, we can leverage actually either an IGP or a BGP. Cisco highly recommends using an IGP, OSPF, or ISIS. And you know, BGP is not recommended by the Cisco documentation. There are plenty of articles on this topic that explain why BGP is not recommended into the underlay. I will probably do a video to go through those articles, but for the moment, just let's have in mind that an IGP is the way to go. And really, honestly, knowing that all we need here is building adjacencies between the leaves and the spines and advertise loopbacks inside. And IGP, you know, it makes sense because we just need to configure adjacencies like router, enable router the process for OSPF, and you know, configure the loopbacks inside the process, and it's done. It's really straightforward. I mean, BGP is really kind of overkill for this use case. So yeah, this is all for the underlay. Now let's head to more details for the overlay, because now that we have our reachability between the edge devices, so between the leaves, we can start attaching the workloads to our leaves and announcing this information, so the reachability information of the workloads to the rest of the fabric through what? Well, obviously, through the overlay. So now I hope it all makes sense for the pieces of the puzzle fitting together. Let's continue with the terminology. What do we have inside each leaf? Actually, we have something, another thing actually that we introduced in the previous video, which is the VTEP, so VXLAN tunnel endpoint. So the way I like to see it, like the leaf, it's kind of two personalities inside one box. What I mean by this is that I like to see the leaf like a bottom part that resembles to a kind of classic layer 3 switching that is capable of doing switching and routing and is responsible for attaching the end hosts. Actually, it can be hosts, it can be servers, it can be load balancers, service nodes, routers, and anything. We can attach anything to the leaf and it acts as a layer 3 switch. And I like to see the upper part of the leaf as the VTEP, so the VXLAN tunnel endpoint. And in the down part, we are receiving quote-unquote naked packets, meaning the packets that are really sent by the end host. And the upper part, here we are encapsulating the traffic from the end host to the rest of the fabric and also decapsulating the traffic from the fabric to be forwarded to the end host. Obviously, we do the two. And inside each VTEP, we have what we call an NVE, so a network virtualization edge. And by the way, when we configure the VTEP on the Cisco Nexus 9K switches, it's not that we create VTEP context or something like this. Really, what I said before, it's just a way to see it, to represent it. It's not like this in the inside, okay? The way we configure the VTEP is simply by going to conft and configuring actually the interface NVE. So all the configuration of the VTEP lies inside the NVE interface configuration. And on top of that, what do we have is obviously the tunnels that we will build between the VTEPs. Each tunnel, we can name it as a virtual network, and each virtual network has its own identifier, which is the virtual network identifier, right? It makes sense. Or another term, it is the VNID, the virtual network identifier as well. It's just VNI or VNID, depending on the documentation that you will be considering, you will find one of the two. Now, we are going to see again and again, actually, all these blocks, but each time we will see it in more details, because at the end of the day, here we have already spoken about plenty of stuff when it comes to the capabilities of the fabric. We have covered a lot of elements, but how it works under the hood, this we need, of course, to dig more. And each time, actually, we will be taking the same slide, the same drawing. It's just that we will check it from a different perspective by mentioning other key elements, other key points, right? So let's head back to our slides to see what will be occupying us for the next probably 15 to 20 minutes. It's explaining all this stuff that is summarized into this slide. So the control plane responsibilities and the data plane responsibilities for the overlay. Because again, the underlay, we have seen it, it's straightforward. Let's say OSPF protocol announcing all the loopbacks. We have the reachability of all the loopbacks done. This is the underlay. The overlay, it's another story that we'll be going through now. So good, let's see all this point by point. And we take back our beautiful fabric and we are going to see the first point, which is the route learning, the route distribution, and the peer discovery. Just before this, I want to make a disclaimer. As I have mentioned, here we will be considering that we have OSPF as the underlay and all the Nexus devices being into the same AS. And this assumption, by the way, it is really the case of almost 100% of deployments of Cisco VXN, L2VPN, EVPN fabrics. So we usually use IGP in the underlay, and then iBGP for the overlay. So it is iBGP, L2VPN, EVPN in the overlay. I know I mentioned it multiple times, but really I wanted to have our IDs crystal clear on that. Everyone inside this site is in the same autonomous system. So now we are going to be able to see the roles of everyone. So first, the responsibility of each leaf, the first responsibility of each leaf is the local learning. What does it mean? It means that when the attached devices will start sending traffic, whatever the kind of traffic, and it reaches the ports on which the local device is attached, the leaf will learn the MAC and the IP. I know it's a bit small, but hopefully you can distinguish that here I have MAC1/IP1 connected over Ethernet 1/1. And all the leaves in my fabric will do exactly the same, meaning each and every leaf will learn about its locally attached end devices. You might ask yourself the question, what about the silent hosts? We can cover the silent hosts. By the way, we will cover the silent hosts in a further section, not in this video, but in another one. In any case, the key takeaway, we know how to handle the silent hosts. Come back to our slide. So for example, the leaf 2, it will learn that MAC2/IP2 is reachable over its attached interface 1/5. And then the host, where is my mouse? The leaf N will learn that MAC3/IP3 is reachable over its locally attached interface 1/12. So this is what we call the local learning. Then we will have the remote learning kicking in. So here, how does the remote learning works? It's using the adjacencies that are built over through the fabric, and it is BGP, L2VPN, EVPN adjacencies. BGP, L2VPN, EVPN. And actually it is an iBGP because we are in the same AS. So I would like to take the opportunity of this slide to stress multiple things because this slide is really important. And by the way, one more time, we will dig into all the details as we go on, especially as we go through the RFC, because we will go through some parts of the RFC, right? It's important. So we will have BGP adjacencies to announce the reachability information. As you might know, initially, BGP was designed only for IPv4. It was BGP4, basically. And then the community of the RFC, the contributors, they built MP-BGP, multi-protocol BGP. So the purpose of MP-BGP is to be able to advertise other kind of reachability informations on top of, other than IPv4 addresses. For this use case, it is a special kind of MP-BGP that we are using. It is the L2VPN EVPN. And in L2VPN EVPN, actually the L2VPN is what we call the AFI, meaning the address family identifier, and EVPN is what we call the SAFI, the sub-address family identifier. And again, we will come back to this when we check the RFC. What I want to stress in this slide is that we only have this kind of adjacencies from an overlay control plane perspective. It is really just this that goes between the VTEPs, really just this protocol. And across this protocol, the leaves will be able to inject absolutely all the information that are learned from the outside. So the MAC the MAC addresses, the IP addresses. Also, if we attach a router with which we build any kind of adjacency, and we learn some external networks from there, also those networks will be re-injected inside the fabric using the same peerings AFI/SAFI L2VPN EVPN. Okay, so this is important. And through this announcement, what we will have at the end of the process, so once all the updates have been sent, once the fabric has converged, it will allow all the leaves to have the same view of everything that is attached. Meaning that, for example, if we take this leaf 2, it will learn about MAC1 IP1. It's just that the next hop is VTEP1, which makes sense, right? It's not locally attached. The same thing goes for leaf N. It will learn about MAC1 IP1, which is reachable through VTEP1. The same will go for MAC2 IP2, leaf 1 and leaf N will learn about it, and same for MAC3 IP3, leaf 1 and leaf 2 will learn about it. And the second thing that I want to stress in this slide is rather for folks who might be more familiar with ACI, who did mostly deployments with ACI, because just a small parenthesis, and I will close it, and we will not come back to ACI in this playlist because it's not the purpose. But in ACI, it's a different logic, at least when it comes to the reachability of the end host, meaning the MAC and the IP/32, so the host IP addresses. In ACI, when everything has converged, the leaves do not know about what is connected to the remote leaves. They don't care, actually. They care only about what is connected locally. Who cares about where the other hosts are connected? It is actually the spines. So the spines are the oracles. So the oracles like in the mythology, not the oracle, the company, meaning they know everything. So when for example, in ACI, when like MAC1 wants to communicate with MAC2, the leaf initially doesn't know where MAC2 is located. It will ask the spine, not ask directly, but there are multiple mechanisms, but basically we will reach out to the spine to know where MAC2 is located. While in our solution here in BGP L2VPN EVPN, from the beginning, every leaf knows the reachability of everyone. So this is what it looks like when it has fully converged, and we see that each leaf has the same database. We can see that MAC1 IP1, MAC2 IP2, MAC3 IP3 are known from all the devices of our fabric, right? Now the second point for the overlay control plane. I have mentioned multiple times BGP peerings. So, well, I wanted to ask a question, but the answer is already on the slide, so it doesn't make that much sense. Anyway, it doesn't make any sense because I'm speaking with myself. In any case, let's come back to the slides. What I wanted to say here is that regarding the peerings, if I wanted to make everyone, if I wanted to spread the information through BGP, I would have needed to build peerings. So iBGP, again, when I speak about BGP peerings, it's always iBGP, L2VPN, EVPN, okay? I will say just BGP for the sake of simplicity, but this is really what I am referring to. It's always iBGP, L2VPN, EVPN, okay? So to ensure everyone's reachability for the host, we would need to build as many sessions, not as many sessions, but it would grow exponentially if we needed to peer everyone with everyone. And on top of that, it would mean that each time I add a new VTEP, I would need to change everyone's configuration in order to account for this new peering. It would work, but it is cumbersome, right? So this is why in Cisco implementation, what is recommended is to have a pair of spines acting as route reflectors. So the purpose of route reflectors is obviously to peer with all the edge devices, or the VTEPs, receive the reachability information for the hosts or the networks that are attached to the VTEPs, and mirror it to all the other VTEPs to the fabric. With this, we do not need to have, you know, to have that many BGP peerings. And here each VTEP has simply two peerings, as you can see, one to the RR1 and one to the RR2. Well, it's not very visible because my slide is dirty, but if we check it more closely, we see that here I have two peerings, right? I do not have an exponential number of peerings. I just need to peer with the two route reflectors. So this is another important point of the control plane. And now we have the last important role of the overlay control plane, which is the peer discovery. The reason why we need the peer discovery is quite complex to explain, and it is related mainly to the forwarding of the BEM traffic. I would like to go first to the next slides. I know it might sound weird, but in the next slide we will speak about the data plane, and we will start covering, I mean, just scratching the surface, because again, it's very complex, the forwarding of the BEM, but we will start speaking about how do we forward the BEM, how do we encapsulate it, and how do we send it across the fabric. And to accomplish one of the steps of this process, we will need the peer discovery. So rather than explaining everything orally, then move to other slides where we will speak again about it, I prefer to move to the other slide, introduce the BEM forwarding, and then come back to this slide if you allow me. So let's put this in parentheses, okay? Virtual parentheses, of course. And let's head to the data plane, the overlay data plane, roles. So, at this stage, the fabric knows exactly where each device is connected, because we have converged and we know that MAC1 IP1 is behind leaf1, MAC2 IP2 is behind leaf2, and MAC3 IP3 is behind leaf n. But now we would like to start sending the traffic from MAC1 IP1 to MAC3 IP3. Let's say that it is a unicast routed traffic. And by the way, even for switched traffic, what I will consider when I speak about unicast is obviously that even for switched traffic, and when I speak about unicast, I take the assumption that the end hosts have already solved the ARP entry for the destination IP. So now what happens when the traffic reaches the leaf? So it is the responsibility of each VTEP to send it to the remote VTEPs. So the way it works, we have covered it multiple times. Again, here I'm speaking about unicast, is that we take the initial frame or IP packet. So let's consider it switched. So this is the initial frame, and it will encapsulate it into a VXLAN header, then into a UDP header, then into an IP header with IP source of the VTEP and IP dest of the remote VTEP. We know how to build this encapsulation, again, thanks to the control plane, because the control plane of leaf 1 knows that MAC3 IP3 is behind leaf 3. So when it builds this packet, it will put its IP address being the source and the IP address of the remote VTEP being the destination. And the same thing, if you want to send traffic from MAC1 IP1 to MAC2 IP2, it will build the same kind of encapsulation and update the source and destination IP address as well. It's obvious now, I'm sure that you get it. So I will now clear my slide and go to the second point, which we have not spoken about so far and is a bit more complex. It is regarding how we forward the BEM traffic. So as an example, let's imagine that we have MAC1 and IP1 who wants to communicate with MAC3, IP3, and let's assume that they are in the same subnet, but the host 1 doesn't know the MAC address of IP3. So it needs to solve it. How does it solve it? Obviously, it will generate an ARP packet. So this time, what leaf 1 is receiving on its front panel port is not a unicast packet. It is a BUM. The destination is 255, etc. in the Ethernet header. So how does it send this traffic across the fabric? Actually, Cisco offers two different implementations for the forwarding of the BUM. The first solution is what is called ingress replication. It is unicast based, and the second one relies on an underlay multicast. So let's check out the first one. So the first one says that it is ingress replication. What it means is that we are taking the initial ARP packet. We are obviously always using the same encapsulation, so it is VXLAN. Okay, this doesn't change. Then we have UDP. Then we have IP. So the IP source is the local VTEP. What about the destination IP? We don't know it, right? By definition, it's not that we don't know it. It is a BUM that we need to send across all the fabric. With ingress replication, what we will be doing is having not one encapsulated frame per ARP packet, but multiple ones, hence the name replication. So we will have this packet a given number of times. Let's call this number, I don't know, not n, because n is the number of leaves, but let's call it x. So x is the number of encapsulated packets that we are creating. And the only thing that will differ between all these packets is the field that we have here. Once it will be the IP address of VTEP2, then it will be the IP address of VTEP3, then it will be the IP address of VTEP4, then the IP address of VTEPN. I'm a bit simplifying here, and I will explain why in a minute. But the goal, you got it. It's that the BUM needs to reach its destination. The destination, we don't know where it is. It can be anywhere. So we need to ensure that all the VTEPs, all the appropriate VTEPs receive this BUM that is unicast encapsulated, that's being unicastly encapsulated to them. And when they receive this encapsulated frame, they will decapsulate the ARP and send it to the to the interfaces that are configured for that VLAN on the front panel ports, right? For the rest, it's really classic layer 2 switching that we have always known since our early ages in networking. There is just one last point that I want to make for this slide, and that will make the connection with the previous slide of the peer discovery, where I was mentioning that it was too early to explain why we need this peer discovery. Here I have said that we send to VTEP2, VTEP3, VTEP4, etc. But there is a lot, there can be tens of VTEPs inside a fabric. And maybe all the VTEPs are not interested, in receiving the BUM traffic. What I mean by this is maybe some VTEPs do not have our VLAN or VNI configured locally, so they don't care about the traffic. Will they still receive it? I mean, will VTEP1 send the unicast encapsulated frame to VTEP5 if VTEP5 doesn't have the VLAN in which the host 1 and the host N are, the host 3 are connected? Well, actually, it will not. And how will VTEP1 knows what are the VTEPs that are interested into receiving the unicast encapsulated BUM frames? It is actually thanks to the last role that we were mentioning in the control plane protocol roles. It is the peer discovery. So there are some kinds of updates in BGP, L2 VPN, EVPN, that will allow to spread the information across the fabric about which VTEPs are actually configured for which VNI. This will allow to build the table of peers that are interested into receiving some kind of traffic. By the way, just a side note that comes to my mind, the peer discovery, I have mentioned it now for the for when it comes to the BUM traffic, but it also plays a role for the discovery of the VTEPs where the remote hosts are connected, because we will discover naturally, thanks to the basic BGP updates, where the other hosts are connected. So these will be also peers. So actually we have not two kinds of peers, but under the hoods, different updates will allow us to learn about the existence of remote VTEPs for different purposes. We will learn about the other VTEPs for unicast traffic because we know exactly what is connected behind them. And we will learn about the existence of remote VTEPs that are interested into receiving a particular kind of BEM traffic. So this leads us to the second point, so the second way of encapsulating the BEM traffic, which is actually, instead of relying on ingress replication, rather using PIM, so multicast-based underlay. And I know that multicast is not something that everyone is happy to work with, but really it works like a charm in VXLAN, L2VPN, EVPN networks. So again, just to put things into perspective, what we are speaking about here is still the same use case that we are trying to solve, which is how do we send BEM across the fabric? In the previous slide, we have seen the first solution, which was using ingress replication, meaning the VTEP creates as many VXLAN encapsulated traffic as he has peer VTEPs interested into that specific VNI. So in ingress replication or hand-end replication or unicast-based replication, it has plenty of namings. The source VTEP will create plenty of copies of the VXLAN, changing only the destination VTEP, and send all the copies across the fabric. With the second solution, it doesn't do that. Each time I look for my pencil. So with PIM, it doesn't do that. So it's either we use either one or the other for each VNI. Okay. So how does PIM work? So how does this solution relying on PIM works? What's the logic behind it? Because the details of how it works, we are not be covering them into this presentation, even though I have a specific slide deck in mind that on which hopefully I will make a video later. So how do we solve this? First of all, let's just for a second forget about the attached host. Let's consider only the links between the leaves and the spines. Here, the idea is that we will build multicast trees, one multicast tree per group. So let's say we have one group, okay? And we will build the multicast tree, sorry, not 239, for example, 001. Let's say that we will build the multicast tree for this group, okay? So we will rely on a rendezvous point. The rendezvous points, obviously, I think you have guessed it will be the spines. So we will build the trees using the rendezvous point. So we will have star, G trees, then S, G trees. We will build the multicast tree for this specific group. Now the question is, what does this group has to do with our VLAN for which we will send the broadcast? Well, actually, the way that the two worlds connect together is at the encapsulation level. Because when the VTEP1 will receive the BEM traffic that is destined for, the BEM traffic for the ARP, what it will do is take that ARP, again, encapsulated in VXLAN, encapsulated in UDP, this never change. Then comes the IP header. The source IP header will be the local VTEP, source VTEP. What about the destination IP header? What about the destination IP in the IP header? Well, actually, the destination IP is the multicast group. And I think that now you got it. We are mapping the BEM of a specific VLAN to a multicast group across the fabric. And what happens is that every VTEP that has that VLAN configured will join the multicast group. So it will be a receiver, an interested receiver for that group. So the VTEP will create the encapsulated frame once, send it over the tree towards the rendezvous point, and then the multicast traffic will flow down using the legs of the tree in order to reach the VTEPs that are interested into receiving the traffic. Then for the end of this flow, it works exactly the same as for ingress replication, meaning the VTEP will receive the encapsulated frame, they will decap it, and get the RRP and forward it to the front panel ports that are interested into receiving the traffic. Now let me clear one more time the mess. And so with that said, let's head to our next pillar into the modern VXLAN L2VPN EVPN fabrics, which is a distributed anycast gateway. So we have seen that one of the advantages of the modern fabrics is that we can have the collapsed functionalities of access, distribution, and call layers all contained into the leaf devices. But not only this, but we can also have the same IP addresses for the gateway and the same MAC address for the gateway configured absolutely everywhere. So this is what we call a pervasive gateway. And this advantage brings also plenty of other advantages, is that we can do seamless seamless VM mobility, because if we take a VM that is, for example, a VM that is connected to a given leaf and we move it to another leaf, then we simply maintain its IP address, its gateway's IP address, and the correspondence between the IP and the gateway, the IP and MAC address of the gateway, meaning the ARP resolution. We can do really seamless VM mobility with absolutely no issue. On top of that, there is absolutely no need for first hop redundancy protocol. It works, the pervasive gateway works thanks to the building blocks and to the implementation that we have of L2VPN, EVPN, and VXLAN in the Cisco Nexus 9K switches. And the last point that is also important is regarding the database of ARP entries that each leaf maintains. Actually, each leaf needs only to maintain the local ARP entries. So the leaf needs to know the correspondence of MAC and IP just of the attached locally connected devices. How does it do for the remote attached devices? This will go into more details as we move on. So in other words, if I have multiple SVIs, I will simply configure for example, let's consider SVI 101 with 192.168.10.1. So this IP address will be configured everywhere. And if I consider the second SVI, it is exactly the same logic. So this is how things will translate. So we configure our two interface VLANs, we put the VRF, and we give the IP address. And the last point is that we configure fabric forwarding mode anycast gateway by giving the MAC address. So the MAC address actually is a global configuration line that gives the same MAC for all the SVIs. And when we configure this, what it allows us to do is enable or activate the SVI as being a pervasive gateway or across the fabric. And this configuration block, we will have it configured on all the leaves of the fabric. It is really a similar kind of template that we are replicating everywhere. And when it comes to the resolution of the IP to MAC correspondence for the for the default gateway, it is very simple as well, because each host solves it locally. There is absolutely no need to send it across the fabric. So the resolutions of the ARP for the gateway is always local. It's 1 to the nearest. We never have any ARP request for the gateway going across the fabric. So with this, we have covered the logical building blocks of the fabric. We have seen in more details the role of the control plane, the role of the data plane for the underlay, for the overlay, and how the reachability information of the host is spread across the fabric, how we reach the VTEPs, etc., etc. For the next video, what we will be doing is check again the underlay, but this time from the perspective of the configuration. So we will see really the CLI behind the way that the underlay is built. And we will also start checking exactly what are the interfaces that we will be configuring on the leaf and the spines, because we have seen multiple times and we have told that For the leaves, they have IP addresses to build the control plane, to build the tunnels, the end-to-end tunnels. What are these IP addresses? What are those interfaces? How do we configure them? So on and so forth. All this in the next video. Thanks a lot for your attention and see you there.